Hello, math people. It's Ken the Metal Professor. I'm with video number 3 in Metal Professor's math coaching sequence of ghost course videos. Ghost courses, meaning I'm trying to shadow courses as the normal U.S. system fall semester is underway. It's at the very end of August for me when I'm making this, and I've been in the previous videos just setting some pieces in place so that when we start talking about calculus, whether it's 1, 2, and 3, you have some of the fundamental tools at your fingertips by having reminders through these videos. So especially in Calculus 1, the ability to handle lines is crucial. So much of the story in early Calculus 1 is about lines, equations of lines, slopes of lines, etc., etc. So here, let's just take a quick tour as a reminder of how we construct and handle equations of lines. Nothing serious, just to brush the dust off. And then the next videos I put out, I'm going to start going from reminders of previous knowledge to getting into topics that are going to be encountered in Calculus 1, 2, and 3 as you go through one semester from beginning to end in a traditional or standard kind of US style calc course. So you can follow along and hopefully get some help, find something useful along the way. So let's talk about lines, because as I mentioned, as you're taking calculus, you need to be able to deal with lines. There is no way around it. Fortunately, lines are relatively straightforward. So the equation of lines that you are certainly the most familiar with is what we would call the slope-intercept form, y equals mx plus b. Everybody knows this one, right? M is the slope of the line, which is a measure of how steep it is. Positive means you're going uphill as you move to the right. Negative means you're going downhill as you move to the right. B is the intercept on the y-axis. It's like the little thumbtack. You go up the y-axis to whatever value is there for B, put in your thumbtack, and that's where the line is anchored. And then from that point, the slope tells you how the line is trending. It's the most familiar line, but it's the least useful equation of a line. The more useful equation of a line is the point slope form. You still need to know the slope of the line in order to build this, but instead of knowing the y-intercept specifically, that you would need to know to directly build a slope-intercept form for the equation of a line, any line will do. Any point will do. And then looking backwards, if you have the equation of a line which is written out in point slope form and it hasn't been multiplied out or shifted around, not only can you see the slope right there in the equation, but you know one point on the line that was used to construct the equation, and sometimes that can be helpful as well. So if your favorite equation of the line is y equals mx plus b, right? You've known that since like 6th grade or 7th grade, probably, maybe 7th grade. 6th is probably overdoing it, but you can pick out the slope of the line, whatever value sits there for m, and b reflects the y-intercept. So if you're given an equation, you can draw the line, right? You go to that point on the y-axis, plunk, put your thumbtack there, and then take out your ruler and draw a line that has the slope that matches m from that point. You can draw the line, but at that point, what are you going to do? Now, in the reverse direction, to build the equation of a line with certain data, if you're going to try to go right for this one, you've got to know some pretty specific information about that line, and chances are you're not going to have it. Okay, so it is much better to start, if you're constructing the equation of a line, go with the point slope form. Okay, and if you're going to anchor yourself in the point slope formula for the equation of a line, you're going to have ingredients. All right, you either need to know one point on the line and a slope, or you need to know 2 points on the line. As you're taking calculus, you're going to encounter scenarios where you might have one or you might have the other. So you're going to have to be able to juggle both scenarios. Easy scenario. How about a line that goes through the point 2, 3 and has a slope of 1/2 again? If you're bound and determined to create the y equals mx plus b version of the equation of this line right away, That's not going to be so straightforward because we don't have the y-intercept. So again, the point slope formula is the way to go. In order to appoint numbers to go into that point slope formula, we have to assign the names, right? Normally the anchor point is x0, y0. In this case, it's 2, 3, and slope m, right? M for slope, go figure, but it is what it is, and we're kind of stuck with it at this point. M is 1/2. And so as we go revisit the point slope structure or template for the equation of the line, there are 3 places that we need to drop in numbers. And we have those 3 values based on the equation of the line, right? Now, this can be a little bit confusing as you circle back around to equations of lines or of other things, to remember that when you're given a template for the equation of something like a line, a couple of parts in that template, like this y that leads it off and this x right here, those are the variables that have been put in place and need to stay in place. Those are not spaces where you're going to plop in numbers right away. But the 3 other locations, the y0, the x0, and the m, those are spots waiting for numbers to get plunked in. We have those 3 numbers. So let's put in y0 is 3. Let's put in x0 is 2. And let's put in the slope of 1/2 right there for m. Make sure you note that these minus signs are built into the template. Our coordinates are positive, and so we end up with y minus 3 and x minus 2 as those terms. Now again, this is a perfectly good way to leave the equation of your line. If you don't have a reason not to, just leave it like this, because right in front of you, you see a slope and you see a point that you used to construct this equation. There may be scenarios where you want to multiply things out and put it over in slope-intercept form, or you might need to modify it for some other purpose. But, unless you have a good reason to, just leave it like this. This is the perfectly good version of this equation of the line. Now, if you're bound and determined to get it in that slope-intercept form, fine. Multiply out the right-hand side, and then add the 3 from the left over to the right, and now we have y equals 1/2 x plus 2. Here's a picture of that line. Remember, the original data was we had the point 2, 3, that's right here. And we had a slope of 1/2. This line is going up. It's rising by 1 unit for every 2 units we move to the right. So there's your slope of 1/2. And when we did our little rearrangement, we did discover that the y-intercept wants to be plus 2, and there it is. Okay, so everything is consistent. So what if you don't have the slope right away? What if you're just given 2 points? Now, this is the natural way to draw a line, right? Have a point right here, you have a point right here, take out a ruler, boom, there's a straight line connecting those 2 points. So that's sort of the geometrically natural way to come up with information about a line. What do? Well, here's a line that has 2 points, -2, -3, and 4, 2. What's its equation? Well, if we're going to go to that point slope formula, we have to decide on the slope, but we have the information to do that. You probably remember the slope of a line is delta y over delta x, or the change in y coordinates over the change in x coordinates. Get used to this kind of structure, delta y over delta x, because in calculus, this thing right here is going to cause you grief for weeks. It's going to be modified a little bit, but keep in mind this idea of a small change in a y coordinate versus a small change in an x coordinate, because that's going to come back at you. I won't say more about that right now. I don't want to overload. Now, delta y, the space between the y coordinates. The y coordinates are -3 and 2. Do we subtract the second from the first or the first from the second to get delta y? It doesn't matter, as long as you're consistent in the numerator and the denominator. So what I've done here is I've taken the coordinates from the second point, 4, 2, and subtracted the coordinates from the first point. So for the delta y, I have this 2 minus this -3, okay? And that's 5. And then for the delta x, I have this 4 minus this -2. Altogether, that's 5/6. Now, I could have done for delta y -3 minus 2, which would have been -5. And for delta x, I could have done -2 minus 4, which is -6. -5 over -6 still simplifies to 5/6. So just be consistent. Don't stress over, oh, is it this one minus this one, or is it this one minus this one? Just pick one and make sure you do the same for the numerator and the denominator. The slope of this line is 5/6. Now, to use the point slope formula, hey, now we've got the value to put for m. Now, gosh, which point do we put in for x0 and y0? Well, we have 2 points. Oh, man, I can't remember which one to use. It doesn't matter. Just pick one. Okay? You'll get the same equation of the line no matter which point you put in there. So with a slope of 5/6, I've picked the point with x coordinate 4 and y coordinate 2 to put in down here. And again, if you don't need to change it and you're happy with this equation of the line right there where we're at, just leave it. You see the slope, you see a point that helped you construct that equation. That's good information. Let it sit and rest. Okay. But if you must go to y equals mx plus b, right? Some simplifying. Whoops. I accidentally triggered the video editor counter there. I'm going to wait for it to go away. There it is. So 5/6x minus 4/3. And again, a picture. Let's look for a y-intercept of negative 4/3. There we go. And a slope of 5/6, which is almost 1. So it's almost a perfect diagonal, not quite. And remember, the original points were -2, -3. There we go in the lower left. And 4, 2. And there it is. So everything is consistent along that line. Okay. Now, when we get to calculus, you're going to go back to this business of finding equations of lines, but often it's not going to be quite as clear where the information's coming from. We kind of sneak up on lines sideways. Here's an example. Go to the curve of the function y equals sine of x and stand at the origin, and then look out to the point on the curve that has an x coordinate of pi over 2 and connect your location at the origin to that point on the curve that has an x coordinate of pi over 2. What's the equation of that line? Okay. There's nothing here about really full points, slopes, anything like that, but we have to be able to extract the information that we need. We still need 2 points. Fundamentally, that's what we're at. So if we're at the origin, one of the points is 0, 0. And if we're going to go out to the function y equals sine of x, where x is pi over 2, the y coordinate of that point is going to be the sine of pi over 2. Okay, you got to know these. That's 1. You don't have to know every trig value that there is, but there are some markers. X equals 0, pi over 4, pi over 2, pi, 2 pi. Your life is so much easier if you learn those. Just a small set of data will ease the skids for so much stuff you have to calculate in calculus. Okay, so we're looking at the points 0, 0, and pi over 2 comma 1 as our data. So we can calculate the slope, delta y over delta x. The slope of this line happens to be 2 over pi. We can go to the slope-intercept form, the point-slope form, plug in the slope of 2 over pi, plug in the origin of 0, 0. I could have also plugged in this point, pi over 2, 1, but why use numbers that aren't 0 when numbers that are 0 are available? Zeros are always better. Okay, and that simplifies to y equals 2 over pi times x. And here's a picture of that scenario. The blue curve is the sine function. There's our point at the origin, the black dot. The red dot is the point at x equals pi over 2. Remember, that's 1.57. Yeah, okay, I believe that's pi over 2 right there. And so this black line is that straight line. Okay. So we had to come at the equation of this line kind of sideways because we started off by talking about y equals sine of x. What does that have to do with the line? Well, we were actually able to pick 2 locations on it and connect them with a line. Now, if you want a sneak preview of something you're going to learn how to do in calculus, imagine that this red dot is a roller, right? And this black line has a particular slope. We just calculated it's 2 over pi. What if we take this red point and move it on the curve a little bit closer to the origin? Now we have from this point, say at x equals 1, we have a new line connecting to the origin. What's the slope of that one? And if we take the red point and move it closer to the origin on the curve and connect that to the origin, there's another line. What's that slope? And can you make a prediction about what the slopes of these lines are going to be as that second point, that red dot, rolls towards the origin to the point where it just collapses onto a single point? Because all your life you've been told you need 2 points to construct the equation of a line. In calculus, we're going to learn how to find the equation of a line that goes through a single point with some other information, but it's a pretty cool twist. Okay, so as you get into calc, make sure that you are comfortable with the basics of equations of lines, and that's going to relieve a lot of stress as you get underway.